Hello, this is the third and final project report for Team Lazarus, which comprises Lydia Green, Zach Shearer, Amanda Montuvaro, and Stephen Silverman. Like our team namesake, we've miraculously risen and produced a workable question asking and answering system. We begin with the asking module, since there isn't that much in common between the two. The first thing we do is split the given article into sentences using the base NLTK tokenizer. Then we parse each sentence with the Stanford parser and extract the most likely parse tree. After that, we iterate over each sentence and try to produce relevant questions from every one. However, some sentences just don't cut it, and so we have to get rid of them before really getting into the weeds. For example, sentences that don't have both a noun phrase and a verb phrase don't lend themselves well to identifying facts, so we eliminate them. We also reject sentences that are too short to contain good information, too long and complex to be tractable, or have too many pronouns, since coreference resolution is difficult and often inaccurate. If a sentence passes all our checks, we look at the noun and verb phrases within it and start creating questions. We have two main types of questions: identification questions and yes-no questions. For identification questions, we find a relevant noun, proper noun, or pronoun and replace it with the appropriate WH question word. We then reconjugate the main verb from the verb phrase and invert the sentence to move the WH word to the beginning, thus preserving grammaticality. We use the pattern library for reconjugation. For yes-no questions, we just reconjugate the proper verb and add a modal verb to the start. We randomly replace proper nouns with other proper nouns to create questions where the correct answer is no, while leaving alone yes questions. Lastly, since the parse tree often tokenizes to a greater extent than just words, for example, the apostrophe s's would get split, we run the Moses detokenizer on the remaining tokens to condense them into a fluent, relevant question. That way, when we join the leaves of a parse tree together, we don't get spaces between things that shouldn't have spaces between them, like the base word, an apostrophe, and an s in a possessive. We mostly tested our question generation system manually, just by looking at the output when we ran the system under different parameters and comparing how fluent and reasonable the questions were in those different scenarios. We tried a lot of different approaches to generating questions, including about half a dozen different parsers, but we found that this one best hit the balance between simplicity and complexity. Our answering module follows a different approach. Rather than parsing the entire article, we just tokenize it into sentences and then use the text blob module to turn each sentence into a bag of words and combine these into one larger bag. We also stem the words so that the frequency counts within the bag more accurately represent the topics that we're talking about. Then for each question we're asked, we first parse it, again using Stanford parser, to extract just the substantive part, that is getting rid of question words like what and where. Then we stem the rest of the question and convert it to a bag of words representation like before. Once the pre-processing is done, we iterate through every sentence in the article to find the most relevant one. For every sentence, we calculate the total TF-IDF score on the stemmed words in the question. That is, take each term in the question, calculate term frequency within the sentence, and calculate inverse document frequency within the article. We adjust the weighting on the term frequency calculation to control for very short or very long sentences, leveling the playing field somewhat. By adding up TF-IDF scores across each word in the sentence, as seen here with sample values, we get a single score for each sentence. Once we have the sentence with the highest TF-IDF score, we simply return it as the answer to our question. Our system is supposed to have three goals in mind for answering questions: correctness, fluency, and concision. We decided that correctness and fluency are far more important than concision, and since any attempt to shorten up the answer by extracting only a particular subtree from the parse runs the risk of both making the answer incorrect by cutting off the relevant information, or ruining the fluency by messing with the sentence structure, we decided to just skip that part entirely. As such, we rely on Wikipedia's excellent community of editors to provide us with well-constructed sentences and simply return the one that's most likely to contain the relevant answer. We tested our answering system also manually, but this time we took advantage of the questions and answers provided to us that were generated by teams in previous years of the project. We looked at the answers that were generated for those questions and how correct they were and how well they matched the answers that our system generated, and tried to tune our parameters and our algorithm to better provide more accurate, more concise, more fluent answers. More accurate, more concise, more fluent answers. Thanks for watching.